All right. Let's see. I haven't decided yet. I guess I need to figure this out on the take home. We talked about that take home thing that either I'll give it to you tomorrow if you do Monday. More likely I may give it to you on Friday, do Tuesday. Tuesday will probably be the day that we do the quiz over the rest of chapter 4 here. Well, it's actually kind of over all of chapter 4, but it's not, you're not going to be doing the optimization. I mean, now we have the take home, like some related rate optimization thing. But on the chapter, I call it just a chapter 4 no calculator quiz, but it's just about the ideas of chapter 4. For example, when it comes to optimization, I might ask you a question, where are the 3 places you look for a max to find a global max or min? What would be the answer to that? Endpoints, slope of 0, slopes undefined, right? Or f prime 0, f prime undefined, and the endpoints, right? Now, is that 3 places? Do the endpoints count as 2? I mean, slope of 0 and slope undefined, those 2 together make critical points. I mean, I suppose you could say endpoints, critical points. I always think of it as 3 places to look. Endpoints, derivative 0, derivative undefined, okay? So stuff like that. So questions about the process of what's going on. The concepts are there. So some fill in the blanks, some true false, some those kinds of things, okay, is kind of what's going to be on there. So like Newton's method. Maybe something about a description of Newton's method, or like number 3 here. Number 3 was, so something that's not really a calculation-based thing, but more of or a computation-based thing, but more of a concept-based. What's going on? What are you trying to accomplish? And so forth in these problems. So number 3, the function shown below has roots near negative 1.88. So that's this one over here, and it has a root near 0.35, which is this one roughly here, and then one over here at 1.53. Which of these roots would Newton's method converge to if x sub 0 is 0.95? So I tried to draw this about as close as I could, but if you go to 0.95, that's pretty darn close to this. 0.95 is pretty darn close to this peak here. So the idea is, and there's really not a right or wrong. If this was on the quiz, I would probably look at the quality of your tangent line here and how you reason it. But the key would be, where does this tangent line go to? And really, the key is this peak right here, right? Because this tangent line looks to me like it would shoot you over this way somewhere. And so if it shoots you to a root, remember, because what does Newton's method do? Newton's method says, let's pick a guess. Let's plug it in, see if we get 0. If we don't get 0, we'll ride the tangent line, which is essentially code for we'll find the equation of the tangent line, we'll set it equal to 0, and we'll find where it crosses the x-axis. And of course, we've made up that little formula to actually do that for us. But that's what that little Newton's method formula is doing. It's like, if you remember how we did it, we took the equation of a tangent line, we set it equal to 0, and we solved for the x. And that's where that little formula came from. Okay, so when we say ride the tangent line, what we're really saying is find the root of the tangent line, find where the tangent line equals 0. So we ride the tangent line to our next guess, and if that one shoots us past this peak, then which one are we going to find? Well, we're probably going to find this one over here, because then this is going to come down to here, and then the tangent line is going to come back up here, like so, and then that's the one we're going to find. Okay, so the key, so if I was doing this on the quiz, it'd be, well, what did your tangent line look like? If I give you the graph, if you had your tangent line coming in and crossing here, right? If that tangent line came in across there, now all of a sudden, your next tangent line would come down here, and then it would probably be here, and then it'd probably be this one that you would find, right? So there was a little bit of talk in the book. I don't know, you probably didn't read that, but there's some talk in the book about this being well, I guess there it is right on page 261. It talks about the butterfly effect, okay, which is a key element of like chaos theory and things like that. Sensitivity to initial conditions. A small change, the butterfly effect, essentially a butterfly flaps its wings on one side of the world, and the ripple effect causes a typhoon, across the globe somewhere, right? So sensitivity to initial conditions. So a minor change in this initial guess could take us from going this direction, whereas if we just go a little bit farther to the left here, then all of a sudden this could take us on this side of the peak, and then we come back this way. Okay, so tiny changes in that initial guess can lead us to find a different route. Okay, so that's the idea behind number 3, and what I might ask you about maybe on a quiz question there. Okay, here's what I got for number 5. I didn't fill it in. I used 0.5. Chloe and I were talking though. She it didn't say where to start in between 0 and 1, right? So let's say, I think you guessed what, 0.25, and then plugged it in and got like -2 something. It's like, okay, that's not very close to 0. So I'm going to pick something else, and that's smart because the farther away you are from 0, probably the more repetitions you'll have to do to find it. Okay, so then she went to 0.75, and that was a lot closer, and so that was less steps. So anyway, I didn't fill it in, but if you start with 0.5, here was the numbers I got. So you really needed, and it's questionable on some of your tables whether you did enough steps. Maybe, I mean, we were supposed to do 3 decimal places, 0.706. The third step here got 0.706 again, so then you felt pretty good about it. I went one more, and I just wanted to show you that, look what happens. You had 3 decimal places in agreement here. I went one more step, and all of a sudden we got 3, 4, 5, 6, 7. We were in agreement all the way out to 7. So Newton's method gets there in a hurry. I mean, it may be a ways away, but all of a sudden it'll find out to a number of decimal places pretty quickly. Because remember, the whole idea is that when you have a tangent line to a curve, oh, that's terrible. When you have a tangent line to a curve, right in that vicinity, the tangent line and the curve are essentially the same thing. If you get in there microscopically close, the tangent line and the curve are really, really, really close to being the same thing. Only at that point are they exactly the same thing, but around there, they're really, really close, out to many, many decimal places, and that's kind of what this is showing. Okay? All right. Whoops, that's for later. All right. And so then 15, you had one of them where it looped back and forth, didn't it, from like 2 to 5 or something like that. And then one of them was way, way out there. Didn't give you a great big huge number or something, right? So you go out. So that would be the case of a shallow tangent line where it's going to shoot you way, 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 way out there. And it may cross the x-axis somewhere, but it's going to be way long ways away. And it might take a while. Okay, so get your calculators out real quick. I'm going to show you. I'm going to pick on Sam. I think you did it recently. So. All right. So I want to show you kind of how you could shortcut this on your calculator a little bit. Did anybody mess around with this at all? And when you were getting on the tables, I didn't really talk much about it. So let's go ahead and go ahead and log in, and let's do number 5, the one we kind of did there. Let's put that in. So maybe you already have it stored. I don't know. Do you happen to have that? Did you store that in your calculator? Okay. Let's see. Type an M. Just type it. Go to your spreadsheet. Type it. Okay, so let's define f of x. So go ahead and let's define f of x, if you haven't already, as, what was it, x to the 5th plus 4x minus 3. Okay, and then minus 3. Wait, time out. Delete that. I don't want to do that. I want to do the one we did on 15. So x, because I know that's got some roots. X to the 3rd, so x to the 3rd minus 10x squared plus 22x. And maybe you do have this one. Some of you might still have this in your calculator, plus 6. Okay, so let's define f of x to be this. So if you do it with me, you can kind of see it's kind of cool how we can use a calculator. And now let's define g of x to be that derivative. And so 3x squared minus don't think she needs it. Got it. Way to go. Good derivative. All right. Now we want to plug in. So in that one, what was one of the roots you found in 15a? What was one of the roots? Okay. So let's put in. We want to put in -1. So one way to do this. Yesterday, this would be of all the shortcuts, this would be the longest way. So let's do f of -1. Go ahead and do f of -1. So let's say -1 is going to be our first guess. So f of -1, hit enter. And then let's do g of -1. Okay. And then what was the formula? It would be -1. So this isn't the table. So what was our formula? It was x sub n plus 1 equals x sub n minus f of x sub n over f prime. Wasn't that it? That's our Newton's method formula. So we're going to take our guess minus this division right here. So we've just done f and g, which is f and f prime. We're going to divide and then we're going to subtract. Okay, so now go ahead and grab f, the -27. Grab that, divide by. Now here's where some people were running into trouble. They were asking me about this. So if I arrow up here to grab the 45, go ahead and hit arrow up. Oh, it did go up. Hit enter. It did bring it down, but now delete that. This was a question that I kind of forgot. Do the fraction. Do control divide. Here's where you run into low. So now go up and grab the -27. Hit enter. Then go down. Now try to grab the 45. You can't do it, right? You were doing that wrong? Yeah. So what happens is you go up to here and then you go to there and it brings it back to the last place you were. So that's where you can copy and paste. So hit delete that and arrow up to the 45. Okay, it's highlighted. So Control C. So you can do Control C, Control V, Control Z is an undo, but you can go Control C, now arrow down and Control V. So if you really need to do this, okay, now you can do that. Now let's hit Control Enter because we want a decimal probably. Okay, and now let's go. So now we type in -1 minus, and then go up and grab our -0.6, right? And hit enter. Okay, so there we go. So this is pretty slow. Now we can repeat that. So the -0.4 is what we want to start with, right? So let's speed up the process here. So let's just go -0.4. Type in -0.4 minus, and now do the fraction. And then on top we'll do f of, and maybe some of you, well, since you were filling out the table, you probably didn't do this because you needed each entry anyway. F of what? -0.4 over g of -0.4, right? And now you get this, okay? Oh, okay, there we go. What did we say it was? It was -0.24 or something? Okay, so, but now we want to do it again. So now let's grab that. So we can grab that, and then minus, and then fraction, and then f of, and now we want to go back up and grab that thing. So we should be able to grab it. Now we want to go down. Now we're not going to be able to grab it. We're going to have to copy and paste. G of, and now we arrow up, copy. Now go down and paste. Okay. All right. And that's all well and good. No, so that's not too bad. Okay. Does anybody have an idea if that's used? Yeah.
It's just put X in the vertical bar.
Yeah. So let's do X in the vertical bar. So now let's go. X. So the formula is really X minus fraction f of x over g of x. Then do the vertical bar outside everything with x equals, now let's go back to our beginning. Let's do -1. Let's see how fast this will work. So x equals -1, hit enter. Okay, and now, let's hit Control Enter. Now what do we want to do? We want to go and change that -1 to a -0.4. So go ahead and grab that, and then change that to -0.4. Okay, and now grab it again, and this time we maybe will delete that, yeah, and then go up and grab that other thing. Okay, we'll have two negatives, there you go. Okay, hit that, okay, so that's a little quicker, quite a bit quicker, actually.
Just do x equals answer.
And now look at the answer key, we're getting closer. So now we go X, so go ahead and grab that thing right there, that thing, grab that, delete, keep deleting, and then, or you probably are, and it's lag, I suppose. You're deleting. Okay. Shoot. We're going to lose it. We were going. Calculator was burning up. Try it again. Okay, there we go. Okay, now the answer, everybody see the answer key, control, and the negative? And what that does, that's just a variable that, so hit control answer. Okay, what that does, that's a variable that just stores the last thing you had, so it plugs it in, okay? And now what happens if she just hits enter right now? Well, we probably got too many decimal places. Let's do this. Go up and grab this. Go ahead and grab that and delete it. Let's start over. And let's put in a -1. Uh-oh. Freeze again. We're going too fast. I can't keep up. Okay. And now now he can go up and grab that. Go up and grab that and change that to answer. Okay. So delete that, hit control, answer. Now hit control, enter. But now watch this. Now that we have answer there, see, even though we have a -2/5 right here, right? Because it said answer, but when she hit enter, it plugged that in. Now watch what happened. Just hit enter right now. See what it did? Since we had this to say x equals answer, that was the last. Remember, whenever you hit enter, it's going to repeat the last entry you had done. Well, the last entry we'd done was x equals answer. So when she hits enter, even though it doesn't say answer anymore, look what it did. It grabbed that and it just put it in there. So now hit enter again. Okay. And now we can see we're way out in a whole bunch of decimal places. And then finally, the way to probably do that right from the get-go is, and this is the way I've done it as well, it's pretty much the same as doing this, is now we'll do this. Just seed the calculator. In other words, let's plant something in the answer variable, -1. So go ahead and type -1 and hit enter. That's going to be my guess. And now I want you to type answer minus fraction, and then what? F of answer over G of answer. And so right now, that's going to take -1, so it's just going to stick it in there. Now hit control enter. And then all you got to do is hit enter. Enter, 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 enter. And then you got it, right? So you seed the calculator with the first thing you want to try, and then you type in answer minus F of answer over F prime of answer, which is, and then boom, 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 and you get it. And it just does all those, and then right away, so you can see pretty close. Now let's do that one that they wanted us to do. So put in 1.39, enter. Now when you do a new seeding, then you got to do it again. So now type answer minus, so we got to type that again because our last entry was 1.39, so it wouldn't work. So answer minus F of answer over G of answer. So that's the one that took us way out there to something crazy. Okay, 5,391, does that sound right? Now hit enter. But look, watch how quickly it brings us back. Okay, so hit enter. So what's happening? I mean, it's still way out there because we're on this cubic, and so we're not very close to 0, but we keep going, right? Now that'd have been a real pain with a lot of hand calculations. Obviously, if you'd put in 1.39 and got 5,391, you'd have picked something else. You wouldn't have kept going if you're doing it by hand. But then all of a sudden, there we go. Okay, and we get back. And so you can just imagine those tangent lines, way out there in this cubic going way up, and then it comes back down, and then it goes way up, and it comes, tangent line comes back down, it goes way up, comes back down. But it's getting closer and closer, and it's eventually coming down to the one where the root is. Okay? All right. Matter of fact, I don't have that up. Okay. So anyway, that's what that one would have come back to. And I think that is one of the roots you got in part A, isn't it? 6.438. That's one of them. Okay. All right. So let's go ahead and get, before we get our notes out, let's go to the sample packet here. Sample 2. See if anybody's come up with some here that they wonder about in sample 2. Okay, and remember, when we go over them, it's kind of a dual purpose. We go over these, sure, so you can get some stuff down on your paper, so when we hand you these packets, you've got some work there. But mostly it's the ones you weren't sure about, because you just got to imagine, okay, I know this is scale, but, just think right now, maybe you have a sense through one packet, all the ones you did, how many could you get right on your own? 50%? 50% is okay. That's probably a B. Right? 50% is probably a B. Are you at 50%? With a little over a week to go. Okay, as we get through the packets, hopefully that goes up. Right? That goes up. So the ones that seem really strange is the ones that are like, gosh, I should be able to get this, or it kind of looks familiar, but I need to, those are the ones we want to make sure we talk about. Where you come in individually to see. So yeah, down, what do you got? Number 7. Yeah, and we were just talking about that one before class too. Some people were, we were asking about this. And again, we've done a number of these, and it's one of those things that you just got to keep doing and keep doing and keep doing. I think the giveaway is H. When you have a limit with H approaches 0, more likely than not, it's the definition of the derivative. Okay, it probably looks like that. And what did that mean? Well, it was the definition of the derivative, right? And we did a series of those problems. We did one worksheet page actually, where every limit looked like this, right? Every limit looked like this. And our job was twofold. We wanted to determine what was the original, what was the F that created it, and then what was the A value where we were doing the derivative at. Now, they gave us the A value here is 3. So what function is this here? What function has been plugged into? Absolute value of x. So remember when we would see sine of x plus h, then we would say, oh, that's the x, that's sine of x. Because what we used to say is f of x plus h, remember German short here, what does that mean? You take x plus h, you plug it into the function. So what's x plus h been plugged into? It's been plugged into absolute value of x. So if you see sine x plus h, if you see x plus h cubed, right, that means the function must have been x cubed. If you see e to the x plus h, that means the function must have been e to the x, right, that kind of thing. All right, that's what we're looking at here. So that's the tip-off. That's what you want to be looking for. Now, so I guess Jaden and I were talking about this, and so he was thinking L'Hopital's rule, right? What do you do first? Well, I get it. You plug in a 3, and what happens? You get you let h, you plug in a 0, and you get 0 over 0, and so you take L'Hopital's rule and all that stuff. Now the problem is with L'Hopital's rule is you'd have to do the derivative of the top, derivative of the bottom. Well, the problem is derivative of the top. What's the derivative of absolute value? We don't really have a rule for that, for doing that. So really it's recognition, and then from there it's just a graph. So then it's recognizing, what am I doing? I'm finding the derivative at 3, which means the slope at 3. Well, what's the slope of this graph at 3? What's the slope of the v graph at 3? 1, right? The slope of the v graph at 3 is 1. So that's really all there is to it. So there's no derivative to even do. Now sometimes when you get a problem like this, there is a derivative you can do, right? You can do a derivative. And that can work. So it's not like you couldn't do L'Hopital's rule, but they usually pick one where you can't really, like an absolute value or something like that. Okay, so that's one to be on the lookout for. It can be neat if you know what they're getting at there. If you recognize that, it can be real easy because there's really not much to do from that standpoint. Okay. Another one that I often see along those lines is like this. They'll do something like this. Same difference, limit, h approaches 0, sine of pi halves plus h minus sine of pi halves over h, right? Now, h is like your variable, so the intent there is for you to recognize this is derivative of sine. What's the derivative of sine? Cosine at pi halves. So this would be just cosine of pi halves. What's the cosine of pi halves? Cosine of pi halves is 0. So the answer to this is 0. Now, could you do L'Hopital's rule though? Yeah, you could, because if you put a 0 in for h, you get 0 over 0. So what would L'Hopital's rule be? Now, so L'Hopital's rule, remember, was the derivative top, derivative bottom. Now we're doing the derivative with respect to what variable? H, right? So what's the derivative of this? Well, that would be cosine pi halves plus h, right? And then derivative inside just be 1, right? Because the derivative of h is 1. We're not doing an h prime, remember, because we're doing the derivative with respect to h. So h prime would be dh over dh, right? So that's 1. We're not doing it. This is just a number, so the derivative of that is 0. Okay, so that goes away. And then what's the derivative of h down here? 1. And then what do? Put a 0 in for h. So what do you end up getting? Same thing, right? Same thing. You put a 0, now you put a 0 in for h, so you get cosine of pi halves. Same thing, right? So L'Hopital's rule is not an awful thought there. When you see the 0, 0, you could do that. You could do that, okay? But it's probably a little faster just to recognize it's the derivative, okay? But L'Hopital's rule doesn't work so nice on a function like that is the only thing. Okay, what else? What else? On 5, what's a relative minimum? Local minimum, right? Another word for local. Relative min, local. Okay? Let me change. Yeah, good one. How many points in this interval, negative 8a, does the instantaneous rate of change equal the average rate of change? So this is really all about the vocab, right? What does the instantaneous rate of change make us think of, or what should it make us think of? Derivative. Derivative, instantaneous rate of change, a derivative at a point. So the derivative of this would be e to the x squared times 2x, right? Greater than sign. So that's the instantaneous rate of change. Okay? What's the average rate of change? What should that make us think of? Slope between 2 points. Oops. Average rate of change should make us think slope between 2 points. What 2 points? These 2 points right here. So what we need to do is do the slope between those 2 points. So the way you do slope between 2 points is you plug in usually the second one. So it'd be plug in an a. So that'd be e to the a squared. That'd be the y value. Minus, now let's plug in negative a. Well, when you square that, that's just going to be a squared again. Right? Over a minus negative a. Right? Which would be 2a. Okay? And then the question really is then when are those equal? Well, what's the red equal to? What's the red equal to? 0, right? Because the top is 0. Right, and it makes sense, e to the x squared, but it's probably some even function. You put opposites in, you get opposites out, and so the slope between a and negative a is probably some even function. It's just going to be 0. The slope is 0. Makes sense. So between those 2 points is just 0. Okay, they have the same y value, right? Here's negative a, here's a. They have the same y value, so the slope between them is going to be 0. Okay, so at how many points in between there are those equal? So in other words, it's just like saying when is e to the x squared times 2x equals 0. That's what we got to solve. Well, it's when one of these two is 0. Well, when is e to the x squared equal to 0? Never. Never. E to the 0 maybe would be, right? E to the 0 would be 1. And otherwise, since that's x squared, that's always going to be positive. So that's going to be e raised to something. So it's never going to be 0. So that's never going to be 0. So when 2x equals 0, which is when x is 0. So there's only one time. Only one time are they going to be equal, and that's at x is 0. Now, the graph that I showed kind of makes sense. Now, I don't know that that's exactly what that graph looks like. But how many times is instantaneous rate of change equal the slope between the endpoints. Looks like your graph like that, looks like one time. Okay, that's actually related to a theorem that we're going to learn tomorrow. Slope between the endpoints and the instantaneous rate of change. So we'll talk about that tomorrow. It's called the mean value theorem. Okay, what else? What else?
So is that the theorem that's talking about?
Yes, there you go. So when we get to one of the things I said is we should be able to do all the circled ones, but we have a little bit left in chapter 4 to do. So every once in a while there might be one we haven't quite learned, and 11 would be one of those. Okay, so put a little mark by 11. I don't know in sample 1 if that came up ever in sample 1. Okay, if there was anything in sample 1, I know I gave you a chance to ask questions about it, that packet. So as we learn a few more things, if there's something in sample 1 you're still not sure of, and it's like, oh yeah, that's that new thing, we could talk about it. So yeah, you might just kind of wait on that till tomorrow, and you should be able to do that. Okay? Anything else? Number 8. This function has a horizontal tangent and a point of inflection for the same value of x. What must the value of b? What must be the value of b? Okay, and so these always, these can be tricky whenever they throw in a k or an a or a b, right, into one of these and finding that. And we didn't do a lot of that when we did it. When we were finding inflection points and where's the derivative of 0, we did basic functions because we wanted to get the basic concept, basic idea. Now that we're moving into this is a time to now take those things and try to, look at them a little differently and work at them a little differently. And so that's the key. Do them the same way. Do the same process, okay? And then just remember, b is just a number. And typically what that means is you got an extra unknown, and whenever you have an extra unknown, you probably need 2 equations. If you have 2 unknowns, you maybe need 2 equations. We have x and b here, you might say. So that's why we're going to have 2 equations, because they said horizontal tangent. How do you find a horizontal tangent? Where the derivative is 0. Horizontal tangent, derivative is 0. Where do you find a point of inflection? Where the second derivative is 0, especially on a 4th degree polynomial. Something that's going to be nice and smooth. That's one thing we're talking about today is smooth curves and continuous curves. But something that's nice and smooth, where the derivative of 0 is going to give you horizontal tangents, and where the inflection points are going to be with the second derivative of 0. That's where it's going to happen. Okay, so that's going to give us 2 equations we can look at. So y prime, we start with y prime, so 4x cubed plus 2bx plus 8, and then and we're going to want to set that equals 0, and then y double prime is going to be 12x squared plus 2b, and we're also going to want to know where that is 0. So we're going to want to know both of those things. Okay? So my suggestion probably would be to take this one here, solve it for b, take this bottom one, so 2b equals negative 12x squared, right? And actually, I wouldn't even have to divide by 2. Normally, we probably would, so I'll go ahead and do it. But so b would equal negative 6x squared. Now, what could I do with that? Plug it into the other one. It's the old 2 equations, 2 unknowns. Solve one of the equations for one of the variables, plug it into the other. So now I can just put that right there. Now, this is a no calculator one, right? So 12x squared, I think I got that all right. 12x squared plus 2b equals 0. So b's got to equal that. Yeah, so put that up there. So now we get 4x cubed. So 2, so that'd be negative 12x squared times x would be negative 12x cubed plus 8 equals 0. So negative 8x cubed plus 8 equals 0. You can subtract negative 8, divide by negative 8, you're going to get x cubed equals 1. So x equals 1. Think, did that okay? Subtract 8, divide by negative 8, yeah, x cubed equals 1, so x equals 1. So, but now that's, I almost fell for it, right? It's really easy to do. Oh yeah, C. Now, what are they looking for? They want the value of B. not x. And we're so used to getting that, but so now we gotta take that value of x, we gotta put it back there. Right? So x is 1, so that means b would be -6. So the choice is actually. So again, it's very similar to what we've done with derivative 0, second derivative 0, that kind of thing, but we throw in this unknown, so now it's back to an old algebra thing of two equations, two unknowns. Substitution method, basically. Okay? All right, well, we'll keep working on sample 2 here a little bit as part of today, so let's move on to kind of our notes that we want to talk about today. So we went over the homework here a little bit here. Well, that's pretty much it. We did some stuff in Newton method and then talked about it a little bit, and then we scribbled around it a little bit. Just look at sample 2, right? So, yeah, I'll leave that up. I might leave that up there for the honor advanced math guys. See, this is what. Yeah. All right. So. Don't always do this. Oftentimes on quizzes, I will give you some, I'll talk to you about things that are going to be on it, what you can expect a little bit, what kind of questions, whatever. But I'm going to take that a step further for this quiz. So for this chapter 4 no calculator quiz, I'm going to actually tell you ahead of time 3 of the questions that are going to be on it. Exactly. Okay? I'm going to tell you 2 today and 1 tomorrow. One of the questions that is going to be on the quiz next week is going to be this. State the extreme value theorem. Okay, that's one of the questions. Guaranteed. Now, I'm not going to dock you if you're missing a word, unless it's a really important word that changes the meaning of the theorem, that I might, okay? So probably your best bet is try to kind of memorize them pretty much word for word, but as long as it's saying the same thing. And I'll give you a couple of examples of some things I've heard people write that make it wrong, or that change the meaning. But the extreme value theorem says, let f be continuous on the closed interval AB. Then f has both a max value and a min value somewhere on the closed interval AB. That's it. Sometimes this is worded with an if, in an if then what? If f is continuous on a closed interval AB, comma, then f has both a max value and a min value somewhere on AB. So sometimes people write that in an if then form. If the if part is typically called the hypothesis, okay, and the then is the conclusion. Now you're going to be asked some questions on your homework about this, and it's going to talk about that. Both the hypothesis and the conclusion. Now, let's talk about the theorem just a little bit. It's an existence theorem. It doesn't tell you how to find the max and the min. It just tells you that they will be there. So let's imagine what we have. Now, the key here is continuous. Matter of fact, the title of this section is Why Continuity Matters. So we've talked about continuous. We've even given a definition of what it takes to be continuous. Remember, there were 3 things. The limit has to exist, the function has to be defined, and the function and the limit have to be equal. The function value and the limit have to be equal. That's what it takes to be continuous. Okay, why does that matter? Well, if you know that a function is continuous and you have endpoints, then we know there has to be a high and a low spot. That's what this is saying. Think about it. If you know the graph doesn't ever jump, right, no breaks, no holes, and there's a left endpoint and a right endpoint, if you know that, then there has to be a high spot and there has to be a low spot. Okay, now, a lot of times when we talk about these theorems, what we like to do is we try to disprove them. Now, they can't be disproven. This is a true theorem. This is true. It's been proven. But we try to look for situations where maybe one part happens but the other doesn't. So here's an example I often do. If you get an A in calculus, your parents are going to buy you a car. Wouldn't that be great? If you get an A, then I'll buy you a car. Okay, so now under what conditions am I lying? Under what conditions is that a false statement? Okay, well obviously if you get an A, I buy you a car, it's not a false statement. Okay, what happens if I buy you a car, or excuse me, you get an A and I don't buy you a car? Then I lie, right? Well, that would be the equivalent of having finding a continuous function and a closed interval, and it doesn't have both a max and min. Well, you can look all you want, you're not going to find it, right? This is a true statement, it's not a lie. So under that condition, I'd be lying. Okay, but now let's say you don't get an A. So the promise was, if you get an A, then I'll buy you a car. So what happens if you don't get an A? Well, I know what happened in my house. Well, my house, even if I got an A, I wouldn't get the car. But let's say that was the promise. You get an A, I'll buy you a car. What happens if you don't get an A? Yeah, you go to second chance. What happens if you don't get an A? Do you get a car? Maybe you could, right? Now, again, in my house, that wouldn't happen. I mean, and most of the time we figure, if they say, if you get an A, then I'll buy you a car, you just assume if I don't get an A, not getting the car. But that's actually not what it says, right? If you don't get an A, maybe you get a car, maybe you don't, right? The promise doesn't say anything about what happens if you don't get an A, right? If you get an A, I'll buy you a car. Don't get an A, maybe you get a car, maybe you don't. So, let's apply that to this. What happens if you don't have a continuous function? You could maybe have a max and a min, right? You could maybe have both a max and a min. And you might not. The theorem doesn't say anything about that scenario. So, here's what some of your homework's going to be. It's going to say, does the conclusion hold? They're going to give you a function. It's not going to be continuous, or it's not going to have endpoints, one or the other. So it's like not getting the A. And they're going to say, did the conclusion hold? It's like saying, did you get the car? And so you're going to look at it. So here would be an example. So here's a function. So here would be a function that violates the hypothesis, right? Because it's not a closed interval. Okay? But does this have both a max and a min? Yeah, but we're just lucky. We just got lucky. You know, it's kind of like getting the car. You didn't get the A, but okay. So the extreme value theorem does not promise that there's going to be a max and a min on that example. Okay, but there is. And so on the homework, they'll say, okay, here's this function f. Does the conclusion of the EVT, is what they'll call it, does the conclusion hold? Well, the conclusion is just, is there a max and a min? You'd say, yes, the conclusion held. There is a max and a min, even though there wasn't promised to be. Okay? Horizontal line, good question. It's kind of like, it's a little bit like sine. What's the max of sine? Even though it happens a whole bunch of times, right? So if I have a horizontal line here at 4, and it goes from this endpoint to this endpoint, what's the max? 4, because there's no value bigger. What's the min? 4, because there's no value littler. So it has both a max and a min. They just happen to be the same. Okay? Good question. So, anyway, that one doesn't it violates the hypothesis, so therefore you're not guaranteed to get a max and a min. Okay? But the conclusion does hold. So when you see those homework questions, they say, does the conclusion hold? That's what they're saying. They're saying, does it have a max and a min? It's not guaranteed to, but it might anyway. Right? So the theorem itself is fairly boring. It's like, okay, it's continuous. If it's continuous and it's a closed interval, okay, we got a max and a min. Now, we learned earlier in the chapter where to look for them, right? We looked at endpoints, stationary points, and where the derivative is undefined, right? That's what we look for. But this guarantees us that there will be both a max and min. But look at our optimization problems. We had some where we didn't have endpoints, right? Some we had a max, but we didn't have a min. Well, that's because maybe we didn't have endpoints or whatever, okay? But if we did, and it was a continuous function, then we had to have both max and min. Now, if I change this just a little bit, now does the conclusion hold? Is there both a max and a min value? Is there a minimum value? What if this hole is right here at -3? Is there a minimum value? There it is. Okay, right above it. So -2.9? No, wait, what about -2.99? What about -2.999? What about negative 2.99999? There is no value right above it, right? There is no value right above it, because if I go right above it, I can always come back down a little bit, right? There is no minimum value there. That seems strange, right? Are you kidding me? There's a limit, right? There's a limit. The limit would be -3. The cars meet at -3, but that's not what we're saying. Is there a minimum value? There's no minimum value of that function, okay? There's no minimum value of that function. All right, and then of course you have one that just goes down forever. Obviously there's no minimum on something like that. Okay, and then what if this was an open circle? Fill that in. Does that have a max? Doesn't have a max. Has a min, but doesn't have a max, right? If this y value is at 6, what's its max value? If that open circle is 6, there isn't. 5.9, 5.999, 5.999, you get closer and closer. You can't get there. Okay, so, but these don't violate the extreme value theorem, because the extreme value theorem doesn't promise that those will have maxes and mins. Only if it's a continuous function, no holes, no breaks, no gaps, only if it's a continuous function on a closed interval does it promise that there will be a max and a min value. Okay? All right. Second question I'm going to tell you about the quiz. You know what it is, right? State the intermediate value theorem. Now, extreme value should make you think of maxes and mins. That's how you're going to remember that. The extreme value theorem. It's about extreme values, maxes and mins. The intermediate value theorem, what do you suppose, what's the word intermediate mean to you? In between? Intermediate? I think in between. Yeah, I agree. In between. Okay? And that's what we want to think of. So this one's a little tricky. Let f be continuous on the closed interval AB, and let k be any number between f of A and f of B. Then there exists some C between A and B, so that's input. A and B are inputs. F of A and F of B are outputs, right? A and B are inputs. There exists some C in between A and B, so there's some input such that the output at C, F of C, is equal to K. Now remember, what was it about K? Where was K? I know you're trying to write. Okay, so where is K? Between F of A and F of B. Now remember, those are the endpoints. Remember, A and B are endpoints. So F of A and F of B are our Y value endpoints, right? F of A and F of B are Y value endpoints. So K is between F of A and F of B. So what this is saying, that there exists some C such that its output is between F of A and F of B. Now, you got to almost think of that backwards, because remember, K could be any value between F of A and F of B. So essentially what that says is the function, I mean, if you want to put in quotes off to the side what this kind of says in common language, now I don't want you writing this down as the definition when I tell you to state the theorem. But for your own thinking, you might say that basically what this theorem guarantees, if the function is continuous, is that the curve is going to hit all of the Y values between F of A and F of B. Let me say that again. This guarantees that the curve is going to hit all the Y values between F of A and F of B, which are your endpoints. Okay? So it's a fancy way of saying that. So we're letting K be any value between F of A and F of B. So pick any number in between there. There has to be some input that hits that, is what it's saying. Okay? Let K be any number between F of A and F of B. There has to be an input between A and B that will hit that Y value. Okay? So basically, that's like saying it has to hit all the Y values in between F of A and F of B.
So it's saying that if A, like from A to B, is continuous, that F of A to F of B would also be continuous.
Well, okay, now, okay, I'm glad you said that. They're not two different things, right? The function is either continuous or it's not continuous. So between A and B, the curve, we're saying that the curve has no breaks, no holes, no jumps, none of that. Okay, that's what this first part is saying. So it's continuous. So the function is continuous. So that reminds me, I was going to mention on the other one what sometimes people will say. Sometimes people will confuse, because notice both of these have in the if part, they talk about being continuous on the closed interval. And sometimes people will say, let f be a continuous closed interval. That's wrong. It's not the interval that's continuous, it's what that's continuous? The function is continuous, and that's where I think maybe where you were getting at a little bit there. But so don't say let f be a continuous closed interval, because now you're letting f be the interval, and the interval's continuous. That's not what it is. F is a function that's continuous on a closed interval. So it means from this point to this point, the function's continuous. No gaps, no holes, no breaks, nothing weird like that. Okay, so that's both of these theorems need that. Okay. Title of the section, why continuity matters. Okay, so it has to be a closed interval. So now, what value is this that we know it hits all those? Well, you know what? We actually did this yesterday. Remember yesterday I gave you a function and we were trying to find the roots, Newton's method, and we plugged in a -1, and I don't remember what we got. We got like 1, and then we plugged in a -2. Oh, by the way, yesterday when we did this, we plugged in a -2, and I did it in my head, and I said -3. Yeah, it was -7, and you got nobody corrected me, and so then I go to second block, and I said, oh, this is -3, and they said -7, and I make fun of them. And especially second block, I don't like it. I don't want to look bad for those guys. I don't mind looking bad for you guys, but those guys, come on. And so, yeah, and I said, no, it's not. And I think it might have been Lytle and a couple of them. They're like, it's -7. I was like, no, it's -3. Because I had just done it this period and got -3. Thanks a lot. And they argue with me, and so I said, you got -3 too? Yeah. And so I got -3. And so I sat there and I worked it again and said, oh, crap, it is -7. And I thought, well, God, why didn't anybody correct me? All right. Well, I appreciate you not wanting to make me look bad, but in your wanting to be nice, you made me look even worse. Thanks a lot. Anyway, as soon as we did that, what did we know? We knew there was a 0 in between there. Now, and I said that. I said, oh, okay, you guys said, oh, well, hey, we know there's one in between there. And what I should have said is, are you sure? Because what if that function went, so here's -1, oops, here's -1, 1, right? And here's -2, -7. What did you assume? That it hit all of those points in between. How do you know this function didn't go whoop, and then jump down to here and to do that, right? Well, because it was a polynomial and it was continuous, and therefore we know it couldn't have jumped. That's the only way. So we were using, without knowing it, we were using the intermediate value theorem here. Because between -1 and -2, there's our interval. We know the function's continuous. So therefore, this would be your f of a and your f of b right here, right? We know that this function has got to go through all of the points from here to here. Now, it might go up, come back down. It's not about max and mins. We just know it's going to hit all of the points from here to here. It's kind of like if I drive from here to Grand Island on Highway 30. I got to go through Gibbon. I got to go through Shelton. I got to go through Wood River, right? I got to hit all the points between here and Grand Island, right? It isn't Star Trek. I can't beam myself over there, right? That would be discontinuous. Continuous would be I have to hit all of those in between. Okay? So I have, there's a little picture of this that I could show. Let me see here. If I can find it. Okay, so again, don't confuse max and min. So this is going to find, so the intermediate value theorem guarantees that we will hit all the y values between which 2 points? What values are they approximately? About 1 and, no. We're looking at y values. I'm talking about y. It has to hit all the y values. between 3.5 and 0.7 or so. In other words, between the black dots, we're guaranteed that we're going to hit all the, again, think about driving here to Grand Island. If I start here and end here, I have to hit all the points in between. I might go some other, so if I drive from here to Grand Island, I might go to Elm Creek, right? I might hit Elm Creek. I might go to, Central City and end up in Grand Island. I might have, but if I start in Kearney and I end in Grand Island, I know I got to hit all those points in between Kearney and Grand Island. It might hit some others, but I know I got to hit the ones in between there. So they show this kind of sliding, and it's got to hit the ones in the green area, right? And there's one, and I don't like case bouncing up and down there. It found a couple of them, right? Some C values where, but there has to be at least one. So that's what's going on. Okay, so that's the intermediate value there. All right. So, back, one last thing then. Okay, so, does this function here, does this function, does the conclusion of the intermediate value theorem hold? Does the conclusion of the intermediate value theorem hold? Well, what is the conclusion? That it'll hit all the y values between the endpoints. What are the endpoints? Here and here. Do all the y values between here and here get hit? Well, that's only the y values from here to here, right? Well, sure enough, absolutely. So the conclusion holds. Now, it's not guaranteed to because this is not continuous, right? This is not continuous. But but it did. So I just got lucky. It wasn't guaranteed to hold, but again, it's from here to here. It's between the endpoints. I started here, ended here. Did I hit the ones in between? Yes. Okay. If I change that a little bit and go something like this. So now the curve goes like this and this. Okay, now did the conclusion hold? Do I hit all the endpoints? All the y values from here to here. So do I hit all the y values from there to there? No, there's a gap in here, it looks like, where I didn't have any y values. Okay, so in that case, the conclusion did hold, which is fine. It doesn't contradict the theorem because it's not continuous, right? So, and it may ask you, it may say, does this contradict the theorem? The only way you can contradict the theorem, well, you're not going to. It doesn't contradict the theorem. Why? Because one of the hypotheses was not met. It's either not continuous or it doesn't have endpoints. One or the other. It's not continuous or it doesn't have endpoints. Okay, so you got the 4.8 homework questions on your sheet. Okay, the 4.8 homework questions are about this theorem, and then keep working in sample 2. Okay.